Alrighty, this is going to be a pretty straightforward video um, of watching some ice melt. I took a plastic cup, filled it with water, and I stuck this temperature probe in there. And then I stuck it in my freezer so that the temperature probe is frozen in the block of ice. And all I'm going to do is I'm going to leave this here for a while with the timer running so we can see how much time has passed. And I'm just going to check in with this melting ice every I don't know, every 5 minutes or so, and so that we can see what's going on with the temperature of the ice. You see right now it's reading at negative 0.4 degrees Celsius, and we're just going to check in every so often and see how that is coming along. So fast forward 5 minutes. Okay, so it's been about 5 minutes now, and it doesn't really look like anything's changed. The temperature is still reading negative 0.4 degrees Celsius, and I don't see any change in my ice here. So maybe I should leave it for a little bit longer. I think I'll check in around minute 16, so I'll give it another 10 minutes, and we'll see if anything changes during that time. All right, so as you just saw, or as you just thought about, I guess, even though the ice has been sitting on this desk and certainly absorbing heat from the air around it and from the desk itself and from my hand every time I pick it up, heat is definitely going into the ice, and yet the temperature is still, well, it went up a little bit, 0.3 degrees Celsius. It was 0.4, of course, and we can see that now there's a little bit of water. Yeah, there's some water. So it's definitely the case that the ice is melting, right? Which makes sense because energy is going into the ice, going into the cup. And yet the temperature is still, see, now it's back down to 0.4 degrees Celsius. The temperature is still not changing very much, even as the ice melts. So at this point, I think it might be interesting to start to think about what's going to happen when the ice is almost all the way gone. What do you think is going to happen in, I don't know, maybe another 30 minutes when maybe there's just a small chunk of ice left in this cup? What is the temperature going to be then? At what point is the temperature of this ice water going to start to increase? Because eventually it should end up being about 24 or 23 degrees Celsius. That's about the temperature of the air in this room. So it eventually should equal out, but I'm still not seeing any change from when I first took it out of the freezer. Interesting. Let's check in another 10 minutes. Okay, so now it's been 30 minutes total of this ice sitting here on the desk out of the freezer, and we can see the temperature is still negative 0.3 degrees Celsius. And some of the water, more of the ice has melted into liquid water, as we can see there, but still no temperature change. Interesting. Let's go some more time. Let's do like 20 minutes. Let's go 20 minutes. So I'll check in with you when we're at about 50 minutes on the clock. All right, 20 minutes later, and you can see we're now at negative 0.2 degrees Celsius, so we're still below zero, and a fair amount of the water has melted. We can see that that's how much water has melted. Also, we can see that the temperature probe is sticking out of the block of ice just a tiny bit. So we're also reading the temperature of the water. So that's also interesting to note. At this point, I'm wondering whether, I actually just realized this. We're reading the temperature of the inside of the ice block, but maybe the temperature of the water is going to be different. So I have another, well, actually, I think we can just do this. I think this will come out. Yeah, okay. So this will just come out, and we can read the temperature of the water itself without the ice. You can see it is also very, very cold. It is slightly above 0 now that we're reading, but not by much at all. We're reading at 0.3 degrees Celsius. So the outside of this ice block, or like this liquid water, is basically the same temperature as the inside of the ice block. You know, I think I'm actually going to leave this outside of the ice now. So I'll leave it in the water, and I'll leave that there so you can see it. 0.3 degrees Celsius. So the temperature of the water and the temperature of the ice are basically the same. A very, very small difference in between those two things. I wonder how we would compare a particle diagram of this 0.3 degrees Celsius water and a particle diagram of this, if I can get that back in there. I forgot what it was. What was it, negative 0.2 or something? Basically the same temperature. Let's say it's the same temperature, but one is a solid and one is a liquid. But clearly they're different, right? The ice has very different properties than the water does. So what I'd like you to do, and I'm not sure if I can get this to work on the quizzes because I haven't actually made the quizzes yet. I think you're going to have to do it on paper. So sorry about that. But if you could, please get out a piece of paper, and I want you to draw me a particle diagram, and I'll ask to see it tomorrow, so please actually do it. A particle diagram of the ice at 0 degrees, or about 0 degrees, and the water at 0 degrees. How should we draw those two different, if they're the same temperature, but they're different states of matter? See if you can figure that out. And I will check in with you in, I guess, another 20 minutes. We'll see if we can get more of the ice to melt, and we'll see whether the temperature has started to change in any real way. Okay. I'm actually starting to get a little bit annoyed because it's almost 9 p.m. I did not think this would take so long. We're still at 0.3 degrees Celsius. Has not gone up at all since that time. And we are still steadily gaining water. We have a lot more water now, but I mean, yeah, still a lot of ice. But still, you would think that the temperature would increase a little bit. We're still at 0.3. Okay, maybe I'll check in an hour. I really didn't think it was going to take this long. Okay, so it's been an hour officially. I still have a bunch of ice in here, and I'm realizing now I probably should have I should have just used less water. I don't know what I was thinking filling this cup up. But I guess I just kind of like underestimated how long it would take for this ice to melt, considering that like this is not an insulated cup at all. It's just a plastic cup, a cheap disposable plastic cup. Let's see what my temperature's at. 0.5 degrees Celsius. So we're still at the same temperature, essentially. By now you might be realizing or guessing that the temperature is going to stay the same as long as there is ice in the cup, which sounds ridiculous because as the ice is melting, we know that heat is going in, so we would expect the temperature to be increasing, right? And surely the ice melting is a sign that the temperature is increasing, or like you would at least think that, but our evidence seems to be disputing that. It's still 0.5 degrees Celsius, even though this ice is definitely melting. Okay, well, it's now 10 o'clock p.m. and I'm starting to question whether I want to stay up for this because it's about my bedtime. But we'll check again. I can't promise that I'll make it for another hour, but maybe I will. 2.5 hours this project has taken. That's longer than I thought. Okay, well, see you soon. All right, it's almost 11 p.m. now. I don't know why I waited so late in the evening to start this video. Because now I don't know that I want to finish it. We're at 0.3 degrees Celsius. We still have a fair amount of ice, you can see. Most of it is melted, I would say. But we still have the same temperature of 0.3 degrees Celsius, which is a little bit surprising to me, honestly. A little bit surprising. That's crazy. I think we probably are going to have to, I think we're going to have to change our definition of heat, you guys. Because remember, the definition that we were using for, like, granted, just a couple days, it was the ability of something to, like, change the temperature of something else. And, like, this room that I'm in right now certainly has heat, right? It has heat, and this desk has heat energy as well, right? Because this desk is like room temperature, you know, it's like 70 some degrees. So, like, but it's not changing the temperature of this ice really at all. It's melting the ice, but it's not changing the temperature of it at all, which you have to think about what that means at the particle level a little bit, because we know that temperature is particle speed, right? So the particles in the ice this whole time have not been speeding up whatsoever. They've been staying at the exact same temperature, the exact same particle speed for this whole time. And what's really weird is that this liquid water, which is what I'm actually reading the temperature of, is like just as cold as the ice. If I stir it around a little bit. It reads the same temperature, 0.5, 0.4, 0.3, in that range. So this water, somehow, we're saying that it has the same amount of kinetic energy as that block of ice right there. Which is weird, right? How can the particles of the water be moving the same speed as the particles of the ice? That doesn't seem right, right? Based on what we know about solids and liquids, they have completely different behaviors. We can see that the liquid particles are able to like slide past each other. And we know that the solid particles are kind of like locked in place. They just like vibrate a little bit, but they have the same amount of energy. Or rather, they have the same amount of kinetic energy. Clearly, this water has absorbed energy, right? These H2O molecules have more energy than these H2O molecules, like in the frozen ice. That has to be true, right? But it just doesn't have more kinetic energy. How could it, if our definition of temperature is the amount of kinetic energy? I don't know. This seems to be suggesting that one or more of the definitions that we used at first might not be completely correct or complete. Maybe there's some other kind of energy rather than just kinetic energy or thermal energy. Like that's weird. There's something here. There's something here that we need to explore a little bit more carefully. You see, like now we're back down to 0.3 degrees Celsius. Okay, well, it's been 3 hours, almost 3.5 hours. There might be another update here. This might be the end of the video. I'm gonna edit it in the morning, I guess, but there might be more. I mean, you can see, because you can see how much time there is left in the video, but I might fall asleep. So we'll see what happens. If not, I'll have some questions here at the end to kind of wrap up this experience. All right, it's been more than 4.5 hours. I'm somehow still awake. 0.9 degrees Celsius, and the only ice that's left is this little piece right here. With all the other ice is melted into water, and our temperature is still less than 1 degree Celsius. We are getting it to change a bit now, but even with almost all of the ice gone, still we're at 0.9 degrees Celsius. I'm almost certain this is the last video until the morning, when the ice will certainly be melted. So I think this is our final update. I wish we could see what would happen once the ice is all melted, but we just don't have time. I have to actually make this video now and write some questions to go with it. Anyway, okay, so this has been interesting. Cool. Alrighty, checking in at 1:38 a.m. It's been 6 hours now. We can see the ice is finally gone. No more ice in here at all. And the temperature has risen quite a bit. We're still pretty cold, 10.9 degrees Celsius. But now the temperature is finally rising clearly. And now it seems to be rising pretty quickly, actually, because we were just at 10, going up fairly quickly now. 11.3. 11.4. So whereas before, when our ice was still there, the temperature was increasing extremely slowly. And actually, we saw the temperature didn't really change very much while the ice was in there. But now that the ice is gone, finally gone, we're getting the temperature to increase much more quickly. Interesting. All right, 7.5 hours. Currently it's 3 a.m. You can see your temperature of our water is at 14.5 degrees Celsius. So still somewhat cool. Should be comfortable water to drink. You would notice that it was quite a bit cooler than room temp water. I'll put this in Fahrenheit just so you can get a sense, a little bit of a better sense. You can see the temperature, 58.8 Fahrenheit, which is still 15 Celsius. So still cool water, but definitely increasing more quickly than when the ice was in there. Okay, so 10.5 hours now, and I truly cannot believe this. The temperature of the water is still not the same as the temperature of the room. I just checked, and the temperature of this room is about 19.6 degrees Celsius. So we're still like almost 2 degrees lower in the water compared to the room. So we had the entire night passed. Right now it's 6 a.m. now. The entire night passed, and the room and the desk had all this time to transfer heat into the water to get it up to room temperature, and it still was not enough time to do that. Still not enough. After an entire night, I'd have to leave this here for even longer. But now I really do have to export this video and edit it together so I can get the questions added. But that is incredible. That is incredible. Water seems especially resilient and resistant to temperature change. Because, like, can you think of anything else that I could have put on this desk, taken out of the freezer and put on this desk, and it would have taken longer to reach room temperature? I mean, no. Anything else I could have put, it would have been in room temperature within a couple of hours, I think. That's incredible. It's still not there after all this time. Wow.